All right, and we're back for the last section before your first quiz. We have section 6.3. Our first quiz will be on 6.0 or 6.1 to 6.3. So today we're talking about binomial radical expressions. Binomial just meaning two terms. And we'll see what that looks like very shortly. Our EQ is how do I add and subtract. So yesterday's EQ is how do I multiply and divide. And today we're going to see what happens if you do addition or subtraction, which sounds easier, but it's a little bit more selective when it works. So as a warm-up, we're going to simplify each of these radical expressions. What we saw yesterday is if you have the same index, you can multiply those together. So I can combine these two expressions into one and then worry about taking the third root of it. So if I multiply 4x squared y to the fourth with 16xy to the fifth, I end up with this, the third root of 64x to the third y to the ninth. And this one's actually really nice because each part of the radical simplifies really nicely. The third root of 64 is, the third root of 64 is just 4. The third root of x to the third is just x to the first. And then we end up with y to the third power. There's nothing left inside a radical because everything was a perfect cube root. So we leave it like that and we move on. This one like this is what we're working on yesterday. If you can't simplify or if you can't square root 50, we're not going to deal with decimals at all. So what we did was we said, all right, if I want the square root of 50, how can I simplify that? What number goes into 50 that I know the square root of? And the only number that does go into 50 that is a perfect square is 25. I can then write this as 5 times the square root of 2. And then if I do the same thing with x to the 8th, x to the 8th simplifies real nice into just x to the 4th, not y to the 4th. And I don't need absolute value here because my answer was an even power, so it was x to the 4th power. And then finally we have y to the 3rd. If I break this up, I can't do, remember, our trick is, can I do the power divided by the index? I don't want decimals. I can't do 3 divided by 2 and get a whole number. So I'm going to split this up into y squared and y to the first, which will then simplify into y times the square root of y. What we did in 6.2 was we then said, all right, let's take all the things that made it outside of the radical, and we're going to write those down first. So we have 5x to the 4th absolute y, and then underneath the square root, we have left 2y. So here's our final answer, fully simplified. Hooray, la-di-da. All right, your homework again from 6.2 was 12 to 45 every third problem. We're going to get right into it. So in 6.2 multiplication division, today we're going to talk adding and subtracting. These two radicals yesterday, or in 6.2, you could multiply those together because all that needed to be true was that the index or what root you were taking had to be the same. In order to add or subtract, though, both the index and the radicand, or the number underneath, have to be the same. So this is truly like combining like terms. We can't combine like terms unless they're both the same root and they have to be the same index. So if you see something like the square root of 3 plus the square root of 5, this cannot be simplified. This is already like, this is simplified to the max. It's something like this where we see how the adding and subtracting works. If I have the square root of 10, we know I can write that as 1 times the square root of 10. So it's basically saying what's 1 square root of 10 plus 3 square roots of 10. Well, if I have 1 of something plus 3 more of something, all I'm going to do is add together their coefficients, and the radicand does not change. So when we're adding or subtracting, if I'm adding root 10s together, that root 10 stays the same. And then I just add the coefficients, so the 1 and the 3. So obviously, like, this is intro to it. We're going to build up a little bit. So of these three sets of expressions, which ones can be simplified? So here we have 7 root 5 minus 3 root 5. They're both square roots. They're both root 5. So I'm just going to do 7 take away 3, which gives me 4. 4 square root 5. We're good. For the next one, we threw a variable in there, but that doesn't change anything. If I have 2x root 7 plus 8x root 7, they're both root 7, and I can add 2x and 8x to get 10x. So that one's fully simplified. And then this is where we get into the fun stuff, the new math for today, is what happens for something like 4 times the square root of 12 minus 5 times the square root of 27. And on the surface, that cannot be combined because 12 and 27 are not the same radicand. And do we look at this? Yeah, okay. So on the surface, this looks like it can't be combined, but what we're going to do is use what we know from 6.2, and we're going to simplify first, and we're going to see that they actually can be combined together. So if you have 4 root 12, I know the square root of 12. The square root of 12 is not a whole number, but I can break up the square root of 12 into the square root of 4 times the square root of 3. Here's what can be tricky. I'm going to bring this 4 that was the coefficient is going to stay out front. And now if I simplify this, I have 4 times 2 times the square root of 3, because the square root of 4 becomes 2. Then I can multiply the whole numbers together, and this then becomes 8 times the square root of 3. If I do the same thing for the square root of 27, I know I can break that into 9 times 3. This becomes 5 times 3 times the square root of 3, which becomes 15 times the square root of 3. And now we see that the radicals that started not having the same radicand, when I simplify, they both are square roots, or they both have the same radicand, so now I can combine them. 8 take away 15 is negative 7. Keep the radicand the same, and there's our final answer, is negative 7 square roots of 3. So don't judge immediately whether or not they can be combined, because you do want to see, can we simplify? If we look back real quick, the first example we looked at, the square root of 3 plus the square root of 5, neither one of those can be simplified, and so that's how we know that nothing else can be done. So go ahead and give this one a shot by breaking down each radical first, and then seeing what can be combined, and then we'll move on. So we know root 20 can be root 4 times root 5. This becomes 3 times 2 root 5. So our first term simplifies into 6 times the square root of 5. 125 is a little bit trickier, but that's just 25 times 5. So this becomes minus 5 root 5. And then finally, we have 4 times the square root of 45. But 45 can be broken up into 9 times 5. And I'm choosing 9 because I know the square root of 9 to be 3. So this was 4 times 3 root 5, which becomes 12 root 5. So now that we simplified all of those, and I have all of these are root 5s, which is perfect. That means I can multiply, or I can add the coefficients. So 6 take away 5 is 1. If I add 12 more, that gives me 13. Keep it root 5, and we're done. Okay. So again, you really want to just break down each radical, then see if you can combine. If these first two were root 5s, so these were both root 5, and this last one was like a root 3, then we could only combine the first two. But as it stands, we have something that was perfect. We could combine it all together and get 13 times the square root of 5. Okay, so we're going to just get into a little bit of multiplying if it has a binomial. Again, a binomial means that it's one term two terms together. So this set of parentheses is a binomial, as well as this. We're basically going to do foiling or a distribution, however you want to think of it, is the exact same way. I am going to write this out. I put this box here. You don't need to use the box method. I kind of like it just to start with because it helps me to keep everything straight. So what I'm going to do is I'm going to take those first two terms, 3 and 2 root 5, and those are going to be the one side of the box, and then we're going to have 4 minus 3 root 5 the other side. This is kind of your Punnett square from bio or genetics. And now we're just going to multiply to get the result in each box. 4 by 3, that's 12. When I multiply this with this, I've got 3 times negative 3 root 5. Because the positive 3 and the negative 3 are not in a radical, I can multiply those together. And the root 5 is the only radical I have. So that would become minus 9 root 5. Again, it's because negative 3 times positive 3 makes negative 9. And we can go from there. So in the bottom row, I got 4 times 2 root 5, so that'll be 8 root 5. And then this bottom right-hand corner, I'm multiplying 2 with negative 3, so that's going to be negative 6. But then I'm taking root 5 times another root 5, right? These are being multiplied together. So it's going to give me the square root of 25. And we know the square root of 25 to be just 5. So this is really negative 6 times 5. So this bottom box is just equal to negative 30. Okay. When I fully simplify it. And now with the box method, we're basically going to combine like terms with the stuff that's in the box. So I have 12 minus 9 root 5 plus 8 root 5 minus 30. Well, it's clear that these are both just whole numbers. 12 minus 30, that's just going to give me negative 18. And then we have negative 9 root 5 plus 8 root 5. They're the same radicands, so I know I can add them together. Negative 9 plus 8 is negative 1. So you can put negative 1 root 5 or just negative root 5. And there's our end result. So if you see multiplication, we're going to distribute the exact same way you would with variables. The only rule is that if it's a radical, you can multiply radicals together. Or if it's a whole number like 3 times root 5, those have to stay separate. So go ahead and give these two a shot real quick. Again, I only gave you the one example because it is distribution. So if you want to fast forward through this or if you feel comfortable with it, that's fine. Also, if you don't want to use the box method and you just want to do straight distribution, you can. I like doing it this way because it helps me to keep everything straight. That's 6 root 6, and there's 10. Oh, this last one's always a pain. This is 10 root 30. If I multiply those together, this is going to be 10 root 36, which is 10 times 6. So this is essentially going to be 60. Then I see that I can combine 15 and 60 to get 75. And I can combine my root 6s. I have 25 root 6 and 6 root 6. If I add those together, it gives me 31 square roots of 6 total. And there's our final result for that. Something interesting does happen here, and if you're skipping through it, it's fine. But we've actually seen, again, when we dealt with complex numbers, we've seen what happens if these things look almost identical, except one's positive and one's negative. Those are called conjugate expressions. So for this bottom box, I have root 3 times negative root 3, which gives me negative root 9, which just comes out to be negative 3. What's interesting what we see is when we multiply conjugates together, if you do 25, if you combine 25 minus 3, that's 22. But then when you go to combine the root 3's, you see that they're opposites. So I have positive 5 root 3's and negative 5 root 3's. So those cancel out, and actually my answer is just 22. And it's not a coincidence. So what ends up happening is if you have what are called conjugate expressions, where the first term is the same, but the second term is opposite, so plus one's positive, one's negative, they end up being, when you multiply it, ends up canceling out the middle terms or the radical terms. And so if I just do straight distribution, this is the same problem we just did, but you'll see that we end up with, oops, this should be minus 5 root 3, and then I get plus 5 root 3, and then minus root 9. These then can be canceled out, so it becomes 25 minus 3, which is 22. So what this allows us to do is it allows us to take two radical expressions, and it allows us to simplify it into a real number, or to get rid of the square roots. Here again, if I distribute, I have 4 minus 2 root 6, and then I end up with plus 2 root 6 and minus the square root of 36. Those are gone. I get 4 minus 6, which is negative 2. So we see if your expressions are conjugates where one's positive, one's negative, you will have some interesting cancellation, and that allows us to go back to yesterday's lesson and do some things we couldn't before. Namely, we saw yesterday, if you have a radical or a square root, third root in the denominator of a fraction, that is a bad look, and we need to get rid of it. Yesterday, we looked at fractions that just had just root 3 on the bottom, or just root 5x. What we want to do now is we want to see, okay, I have this binomial 4 minus the square root of 3 in the denominator, and I don't want any square roots there, so how can I get rid of that? And what some students think is they can just multiply by root 3, because the square root of 3 times the square root of 3 is 9, which is then can just be simplified to 3. The issue with that is you would have to distribute this, and if you did that, you'd end up with 4 root 3 minus 3, and then we'd be back to square 1 because we'd still have a radical on the bottom. So if it's a binomial, this doesn't work. So instead, we're going to use that conjugate that we just saw because of its cancellation properties. So to get rid of 4 minus root 3 in the denominator, I'm going to multiply both top and bottom by 4 plus root 3. Okay. And now you just got to kind of hammer out some distribution. I put the boxes here, so if you want to use them, you can. If I multiply 4 minus root 3 with 4 plus root 3, we get 16, 4 root 3, negative 4 root 3. And then this is negative root 9, which is just negative 3. So all of this together, we see that those are going to cancel out. So my denominator is just going to be 13 here, which is nice because, again, that's our end goal, is to get rid of the end goal is to get rid of the radicals in the denominator. And now we do have to do 3 plus root 7 times 4 plus root 3. So we get 12, 3 root 3, 4 root 7, and then root 21. This is a little messy because as you look at this, none of these 4 actually can combine. And even the square root of 21, I'm only going to break down the square root of 21 if one of the factors is a perfect square. But 4 doesn't go into 21, 9 doesn't go into 21, 16 doesn't. So I'm actually not going to simplify that at all. So this is going to look kind of ugly. I'm actually going to move our 13 over to about here. But our, let's erase this. Our final answer is just going to be 12 plus 3 root 3 plus 4 root 7 plus root 21 all over 13. And again, you might say to yourself, like, that's not simpler. There's more stuff there than there was in the beginning. And to that, I agree. But the fact that we have gotten rid of the square roots in the denominator, not too often will you have a numerator that looks like this. But as it stands right now, that's what we want our numerator to be. So, oh, hey.
Hi, sorry.
What's up?
Sorry, we're interrupting a phone call or something? We're just doing room checks for the speech tournament tomorrow.
Sure.
Is that okay if we kind of just move some stuff around?
Jomi, you're going to be able to see this in class.
Oh, did I just interrupt you making a video?
I am currently making a video.
Dang it.
We're gonna stay. We're gonna not cut this.
It's gonna be in there? Awesome.
Hey, it's Miss Killenden.
Hey,
And there's Jomi.
and Jomi.
Yeah, yay math.
Video.
Great. We're almost done. It's all right. Anyway, so in summary, how to add and subtract rational expressions. We know that we need the same index and the same radicand. It was actually really good timing. Like, had like 60 seconds left. 60 seconds left of recording. This is the second one of the day, so I'm about ready to be done. There's your homework. 6-3. See you.